and he's come to give us his presidential address, which is a great honor for us. Naira is well known as an applied mathematician working in various aspects of industry. He's a chartered scientist and chartered mathematician. He has had many accolades. He has been listed by the Science Council as one of the UK's top 100 scientists, and he holds the title as the 5th most influential black person in the UK, which is fantastic considering that he's a mathematician, and first time one has made it into the top 100 list of influential people of African and African Caribbean heritage. His speciality has been in solving complex industrial problems over many sectors. I'm sure he's going to give us some examples of these things in defense, aerospace, automotive, energy. And he's worked around Europe and Israel as well. So it's my pleasure to invite him now to give his presidential address, and he's going to talk on building a powerful mathematical identity. Just before he starts, could I remind everybody to mute their speaker unless they want to ask a question, and you can also type questions into the chat on Zoom so that we can pick up questions at the end of the seminar. But if you could mute your speakers now, that'll help with everybody being able to listen and not getting feedback. Okay, thank you, Naira.
All right, well, thank you very much indeed, Nick, for that introduction and for inviting me to do this talk. My talk is called Building a Powerful Mathematical Identity. It's one of the common themes of the IMA president to give a talk, and this is my talk. So before I start my talk formally, I usually start off with a little bit of music, and then I'll start my talk formally. Okay, I hope you enjoy. Hello. In June 2004, this event happened. The Institute of Mathematics and its application started a conference called the First IMA Youngers Members Conference. Now, this was what would eventually turn into the early careers mathematicians. The IMA at the time was a bit concerned that it was not addressing the concerns of younger members, of those of under the age of 35. And so it started this conference where what you had is you had 40 mathematicians who belonged to the IMA. They came and had this conference. And this was the first conference that I actually presented at And afterwards, they had a panel discussion about how we could make mathematics much more sellable to the general public. Now, there was one individual there who had a degree from Oxford University, an MSc from Southampton University, and then went on to be like say a statistician for the Bank of England. And he said this about mathematics. He says that he would be ashamed to talk about mathematics at a cocktail party. Hold that thought. What I'm going to do is give you this quote, and it's from Cory Booker, who is a United States Senator, and he said this: leadership is not a position or a title, it is action and example. Now, one of the nice things about being a president is that during the second year, you go around to each of the branches and you give a talk or variations of your talk. Now, I was really looking forward to coming to Scotland, but due to circumstances which I don't need to explain about, I put you this picture of Scotland, and hopefully one day I will come to Scotland when all of this pandemic is over. But in terms of mathematics, what we've now know is that we are entering what's called the era of mathematics. Mathematics has now gone mainstream. In March 2020, I was very surprised to see on the BBC News this differential equation. this nonlinear differential equation being presented. And now the general public now knows things such as algorithms and mathematical modeling. It is in the main, it has gone into the mainstream. But when we come to, let's say, a world crisis, maybe it be COVID or something that happened back in 2008, the world economical crash, financial crash, the question is, can we trust the mathematics? Can we trust the mathematics? The general public, the media are very, very scrutinizing mathematics because, as they say, can we trust mathematics to solve the problems that we are encountering? So let me give you the IMA statement, the Institute of Mathematics and its application. Its vision statement says this: to enhance a mathematical culture in the United Kingdom and elsewhere. So the question is, in building a powerful mathematical identity, we must first understand this. Mathematicians, who are we? I say again, mathematicians, who are we? Now, my name is Naira Chamberlain, and this is my story. Now, my parents, this is my dad, this is my mom, they actually came to the United Kingdom from Jamaica in the 1960s, and they were part of what's called the Windrush generation, yeah? And, you know, they didn't knew each other in Jamaica. They actually met in Birmingham, and a number of years later got married. And this is my dad and this is my mom at my PhD ceremony back in 2014. Now, when I was at school, a careers teacher, I spoke to my careers teacher about what I wanted to be, and I said to him that I wanted to be a mathematician. And the careers teacher told me that I had the physique of a boxer. But my parents told me this, and this has kept with me for a long time, is they said that you don't need anybody's permission to be a great mathematician. And that motto has stuck with me all this while, yeah? And this is my wife, and as Jacqueline, and you know, and she's always been very supportive of me. And so I was hoping that when I was going on this tour, that she'll be brought around. So henceforth, I've just put her on this PowerPoint presentation. Okay, so going on a little about my career, I actually did my first, when I did my mathematics degree, I did it at what was called then Coventry Polytechnic. Now, what was that was, we did, let's say, a 4 years degree, and the third year we would do it out in industry. Now, with me, I actually worked as a mathematician at a Royal Air Force Base. And one time I even got the opportunity to fly an airplane. But in my final year, my project that I was doing was to do with strange attractors, most specifically the Lorentz attractor, yes? And then afterwards, I did an MSc at Loughborough University, an MSc in Industrial Mathematical Modeling. And I wrote a dissertation called The Impact on an Adhesive Joint to see how materials behave in aggressive circumstances. Later on, you know, when I was working, later on, I actually did a PhD at Portsmouth University, and this was to do with looking at networks and combining the networks with the gambler's room problem. And my title of my PhD was called Extension of the Gambler's Room Problem Played Over Networks. Now, with me, I have a real passion for mathematics, and I wear many, many hats. You know, I'm not just only the president, I'm also other things as well. First and foremost, what pays my bills? I am a mathematical modeling consultant. I work for a multinational engineering company called S&C Lavalin Atkins, and there I do mathematical modeling, data science, and before that, in my previous careers, I've worked in a number of sectors, but what I do is I solve real world problems. I've been solving real world problems all over Europe. And, you know, one of the things I take into consider about my career, I consider it very much as a mathematical adventure. I mean, in my time, I've crashed supercomputers, I've been involved in international rescue, and I've even used my mathematical modeling to try to save my favorite football team, Aston Villa. So, but in terms of public speaking, two of my more popular talks are this one, which is called The Mathematics That Can Stop an AI Apocalypse, and this other one called The Black Heroes of Mathematics. Now, what is of interest is that in 2018, I was actually invited to take part in an international mathematics communication competition played over the internet, and I was up against a number of different mathematicians. I had to go through a knockout round. I made it to the final, and I won it. And I was so in 2018, I was named the world's most interesting mathematician. And what I was doing is I did a presentation on the Marvel superhero Black Panther, and what I was doing is showing them a mathematical model of the Black Panther suit. So also is that in terms of charity and outreach, is before I was my PhDs, I used to work in Birmingham. I used to do some work in a number of Saturday schools, teaching mathematics to inner city children. And lately, over the last, let's say 5 years, I have been involved in a charity called Target Oxbridge, which helps young African Caribbean and African students of the African diaspora who have aspirations to go to Oxford and Cambridge to study mathematics or the mathematical sciences. I put on a 2-day mathematical masterclass. So here comes the question. Why is the attitude towards mathematics different in the UK than it is in Europe? So the answer to that is a powerful mathematical identity. I say a powerful mathematical identity. See, when I went to Paris and I stand at the foot of the Eiffel Tower and I look up, you know what I see? I see the names of mathematicians written on the side of the Eiffel Tower. But when I stand at the foot of Big Ben and look up, I do not see no names. I don't see no mathematicians written on the side of Big Ben or any other iconic buildings in the UK. So, and this is one of the, I remember I was questioned, I asked this various question to the London Lord Mayor about it. I was saying, well, how come there are no mathematicians? How come London does not Paris celebrate its mathematicians? Why doesn't London celebrate mathematicians? Yeah. So the question is, why the difference? Is it to do with Brexit? Well, I say no, it's not Brexit. It's more to do with something called Mexit. Mexit. Now, in terms of Mexit, you can have hard Mexit and soft Mexit. So what is hard Mexit? The definition of hard Mexit is when a mathematician no longer considers themselves as a mathematician. When a mathematician no longer considers themselves as a mathematician. Now, so the question is, when can hard Mexit occur? Well, it can occur in different places. It could occur during school, it could occur during university, it could occur during your first year after graduation, or occur later on in their career. Hard Mexit, when a mathematician no longer regards themselves as a mathematician. And then I talked about the second type of Mexit, which is called soft Mexit. Now, the definition of soft Mexit is this: when a mathematician is uncomfortable being a mathematician. When a mathematician is uncomfortable being a mathematician. So, see, but the problem with soft Mexit is that soft Mexit mathematicians actually influence younger mathematicians to hard Mexit. When I was in my career, being a mathematician, I would come across as those who, which I define as soft Mexit mathematicians, and they would tell me, no, you will not have a great career in mathematics. Mathematicians only can go so far, and henceforth they were actually discouraging me about the potential of what I could do as a mathematician. I could have made a decision actually to hard Mexit, and I believe that we've lost so many talented mathematicians because of this. So, if mathematics was put on trial, what would happen? Now, our critics could say something like this: how can we trust mathematics in a world crisis when, one, the public hates mathematics? Yeah, I looked on the website and saying why I hate mathematics. 90%, it is useless. 10%, it is difficult. Two, the media hates mathematics. A number of years, I mean, I watch the TV and I see how mathematics is depicted. It's depicted as a subject that is for you have to be very nerdish, and it is very boring to the general public. The media hates mathematics, and I have been writing so many letters of complaints to the BBC and Sky about their depiction of mathematics. 3, the mathematics community is not very diverse. 4, mathematical skills are not sustainable. You know, I pulled this off the Twitter, where it shows the state of a life, like you know, and it says you're at elementary school, college, and then it shows you what type of mathematics you do. That when you do a job, you're saying you know you hit the peak with advanced calculus, and then you drop all the way down to doing a spreadsheet. 5, mathematics has no USP. Now, this is a picture of the beach at Bournemouth after lockdown was removed, and you can actually see how that beach was overfilled. Now, thing is, I'm saying in here is where mathematicians reside, and what you could have is there's other related domains like computer science, statistics, engineering, physics, data science, operational research. And one have to say, but what is mathematics USP? What can mathematics offer that these other subjects can't offer? Is our USP getting smaller and smaller and smaller as these other subjects evolve and become stronger and stronger and stronger? Number 6, mathematics is like a hammer. It is static and is just a tool. When I've been doing my presentations, presenting mathematics and presenting with fellow scientists, they always consider, one of the things that they say is, we consider mathematics as being a tool. It's like a hammer. You see, the hammer, the same hammer that was used on, let's say, Noah's Ark, the design of that hammer will be very similar to the hammer that was used on the Shard building in London. And that's what we see as mathematics, something that is static, that remains the same. Yeah. And to scientists and to engineers and technologists, they just see it as just a tool, just to use to solve a problem. That's it, full stop. And 7, maths is so unattractive that many graduates abandon the profession. Now, when we have to look at the statistics, when we see those people who actually do a mathematics degree or mathematical sciences degree, how many of those actually do join, let's say, the IMA or our sister organization like the LMS or other learner societies, and make that in comparison to those who do physics? You know, those who actually join the IOP, you see that there is a vast difference. The IOP seems to be able to retain its graduates, wherever what field they're actually going to. The IMA and other mathematical societies, we do seem to have this struggle of actually keeping those graduates. So, and I can go on and on and on and on. So the challenge is this how we wish to enter the era of mathematics? You know, us be dominated by soft Mexican mathematicians? Or do we remember this phrase, leadership is not a position or a title, it is action and example? See, now, one of the first things I did when I became IMA president is I actually researched the other IMA presidents. And if you want to have a look at what I did on the Twitter space, go #IMA past presidents. Now, what you see with the past presidents, they were so diverse in terms of the subject where they came from. I mean, you had people who were involved in the design of the wings for Concorde. You had some mathematicians that were involved in World War II in the sinking of U-2 boats. You have mathematicians who were also president of the Royal Statistical Society and the OR Society. You had mathematicians who actually advised the government on educational schemes. The presidents of the IMA, they showed leadership in the field that they were doing, and it was so diverse, and it was very, very inspirational. But the stories their stories is something that we need to be telling. Now, as for me, like I said, I'm very much a fan of mathematics. I enjoy researching mathematics and a diverse group of mathematicians. Now, I'm going to talk about the mathematicians who actually inspired me to become a mathematician. Now, I remember in the 90s reading this book, Fermat Last Theorem, Simon Singh. Now, as much as I admire Andrew Wiles, the mathematicians that actually jumped out to me was these Japanese mathematicians Shimara and Tamami. What they did in 1955, they actually observed a possible link between two apparently completely distinct branches of mathematics. Yes, they're pure mathematicians, but I like this whole idea of a maverick mathematician stepping outside your comfort zone to solve some aspects of mathematics. Yeah. And also, well, just moving on to showing the diversity of mathematicians I'm into, is this mathematician, Dr. Nazana Lawrence, who wrote this, developed this website called Maths is Good for You. Now, she's very much focused on mathematical education, but one thing I'd say is this: if we neglect mathematical education, what type of mathematicians do we produce? Yeah. And we have this gentleman here. Now his name is Professor Keith Still. Now, very much an applied mathematician, and he's a mathematical modeler. And what he did is that he developed an agent-based simulation to model crowd safety. Now, what impressed me about this gentleman is he had an idea, then he did a PhD based on this idea, then he set up a consultancy based on this idea, and then he went around the world doing consultancy based on modeling crowd safety. Yeah. Finally, a mathematician who inspired me is this Katherine Johnson. Now, Katherine Johnson, that was made famous and popular due to the film Hidden Figures. Now, she was an African American mathematician whose calculations of orbital mechanics as a NASA employee was critical to the success of the first and subsequent US crewed spaceflight. Now, thing is, I knew about Katherine Johnson way before Hidden Figures. She was a very popular and inspirational figure to mathematicians of color, and it's very good to see that her story has actually come into the mainstream through the film Hidden Figures. So, but one thing I would say is that as a mathematician, and one thing I've learned is that mathematicians should never stop learning. Mathematicians should never stop learning. I showed you this figure of the stage of life where you go from elementary school, college, job. Now, this when I put up this on the Twitter, I had this reply back from a teacher from the mathematics department of the Oxford High School, and what they did is they designed an activity based on a spreadsheet as an introduction to further math iterations and a bit of complex numbers. That shows that as mathematicians, we should never stop learning, that we never reach a peak and decline, that we keep going on and on and on. And I was really impressed about this school and these teachers in school, how they want to show the beauty of math and the powerfulness of mathematics. So, in saying that, one thing I'd say is that when mathematics is strong, it makes science stronger, technology stronger, engineering stronger, and the economy stronger. Yeah. If you are going into the field of science, then be a mathematical scientist. If you're going into technology, be a mathematical technologist. If you're going into engineering, be a mathematical engineer. If you're going into economy, be a mathematical economist. But mathematics makes these fields stronger. So, but the question is, for those who lead or talk about mathematics, would you have the confidence to say the following? Now, I was actually invited to a parliamentary event where I had to stand up in front of a number of politicians, as well as other presidents from the learned societies, and as well as PhD students. And what they said to me was, Naira, you have 2 minutes to sell mathematics. And this is what I said. Distinguished guests, ladies and gentlemen, the Institute of Mathematics and its Applications is a professional learned society whose vision is to enhance a mathematical culture in the United Kingdom and elsewhere. In light of this, I wish to make the following statement. Mathematics is indisputably the greatest subject in the world. Why? It is one of the few disciplines that can teach science to scientists, engineering to engineers, technology to technologists, and I can go on and on and on. Mathematics is everywhere and is the lifeblood of any modern economy. Furthermore, a mathematical professor and a CEO of a tech startup firm once said this to me: mathematics is at least 100 years ahead of most disciplines. Is this true? Well, in 1796, the French mathematician Laplace described mathematically the idea of a massive star which no light could escape. Today, we now know this as a black hole. In 1939, Albert Einstein published an article in the journal The Annals of Mathematics, in which he intended to prove that such black holes were impossible. So, in conclusion, Albert Einstein was wrong, and the 18th century mathematician proved to be right. Mathematicians in this room, in today's modern data-driven economy, we are entering the era of mathematics. Who among you will be the next Hannah Fry, the next Andrew Wiles, the next Katherine Johnson, or Ramanujan? Even more importantly, make today be your first step, not your last. Finally, always let the world know that you are proud to be a mathematician. And so I said that, did that parliamentary speech, and a lot of people's jaws were on the floor. And then I had all of these engineers and physicists and biologists all coming up to me afterwards and saying, oh, I want to be a mathematician. I want to be a mathematician. I want to be a mathematician. Because they recognize that the stronger you make mathematics, the stronger the subject actually become. So, moving on. So we have to look at our identity. Mathematicians, who are we? How we see ourselves will influence how others see us too. Yeah. How we see ourselves will influence how others sees us too. Yeah. There will always be critics. Yeah. There will always be critics of mathematics, but we welcome challenge as that helps us to grow. But we should not let our critics limit us and stop us from making an impact. You know, us as mathematicians, we grow when we work outside our comfort zone. So one of the things I say to mathematicians, mathematicians must know their value and worth in any arena they enter. One time when I joined the council of the IMA, there was a certain president of the Joint Mathematical Council, and she sat down and she was doing a talk about mathematics, and she was saying about how mathematics funding had been reduced by a third. And then she goes on to says that when she goes into a party, she describes herself as an educationalist rather than a mathematician. And I put my hand up and I say, listen, with absolute respect, if you cannot defend your mathematics in front of your friends, how on earth can you defend mathematics in front of your stakeholders who are about to slash your funding by a third? Mathematicians must know their worth and value in any arena that they enter. Yeah. So, like I said, and if you can't tell from an accent, I'm from Birmingham, and one time I was doing some volunteering work, teaching at a Saturday school, teaching some mathematics, and I said to these inner city boys, city children, I said, right, just to warm up, let's do some long multiplication, and they started complaining to me, and they said to me, well, Naira, we've never been taught long multiplication, and I said, well, but wait a minute. You are 14, you're 14. In a couple of, 18 months time, you're going to be doing your GCSEs or whatever equivalent. And, you have to know long multiplication. And they said, no, they've never been taught long multiplication. And so, and, and I have to agree with an article written by Rob Easterway, who said this on the BBC News magazine, that mathematics has to move away from blindly following rules to techniques a child can understand. Yeah. So.
Okay. What is 87 times 52 equal to? Quite hard. Think about it like this. Write down the 8, write down the 8, write down the 7, write down the 7, times, 5, 2, 5, 2. Draw the shape. Draw the shape. Draw the shape. Draw the shape. 8 times 5 is 40. 8 times 2, 16. 7 times 5, 25. 7 times 2, 14. Add it up. 4, 6, 5, 1. That's 12. Count a 1. 0, 1, 3, 4. Add the 1 means 5. Bring down 4. There you go. The answer is 4,524.
So I came up with this methodology, this technique, and I showed it to the boys the following week, and they got it. And then I showed it to a different cohort of children the following week, and they got it. Now, after a number of years of procrastination, I decided to write a paper and submitted it to the Mathematical Association. They went through, they reviewed it, and they published it. And so henceforth, it was called Long Multiplication and Percentages Without a Calculator. This actually seeing a problem and actually addressing it. Yeah. And the last time I said it, it was being used over in Malaysia. So again, looking at another example is being a mathematician in an engineering environment. You know, when I finished my master's, I worked in the automotive industry, and I worked for an R&D company. And what we was doing is that I noticed that what we was doing is that certainly for piston dynamics and the lubrication of oil within piston dynamics, they would use something called the Reynolds equation. Now, people know about the Reynolds constant, but not many mathematicians know about the Reynolds equation. Now, this is an equation that's been taken by mechanical engineers and used and taken and is claimed has been theirs. But as you can see, the form of this, you know, this partial differential equation is quite complex, yeah. And so, but when I said, oh, you know, that equation is interesting, can I get into it? What the statement that you would used to say to me is, you're not an engineer. You're not an engineer. The Reynolds equations belong to us. You know, we use the Reynolds equation properly. You're just a mathematician. Yeah. So, but working for that same company, what they wanted to do was they wanted to design what's also called a G-rotor. Now, the G-rotor, what it does is that it's on the left-hand side, you pump on oil, and the oil gets squeezed out onto the right-hand side, and then the G-rotor is this concatenation in the middle. And what the idea is to open up space and then to squeeze space, and the oil gets pumped out. And what they did is that the engineers come up with this new design of G-rotor that was supposed to be very efficient. But the problem is that when they put it into its rig to test it out, it wouldn't rotate. And so they gave it to all the other engineers, and they would do all this computer algebra and computational fluid dynamics, and they couldn't find out why it wouldn't rotate. Then eventually, the last person they actually gave the problem to was me, and they're saying, look, all our engineers have gone through this problem. We're now going to give it to you, a mathematician. Can you find why this is not working? And so I looked at the problem, and I looked at the design, and I recognized that actually how they actually design a G-rotor is that what they did is that they use this this equation here, which is the shape is called an eclipsoid. And what they do is that they take the differential of this eclipsoid, and what they do is by taking the differential or looking at let's say the normal, and going a certain distance along the normal, they can actually create the profile of the G-rotor. But the problem is where the G-rotor had, let's say, these 2 points here. Here it would have two normals or two tangents, and the engineers didn't they say, wait a minute, there are two tangents at this point. And so what they did, they made the assumption that really and truly to create this shape is all we need to do is just take the average, and there's your average normal, and then that will create the solution. But I'm saying, well, wait a minute, you're not actually recognizing vector analysis, and you've actually corrupted your shape. This is why your shape is not G-rotor, is not rotating. And so what I did was I then corrected the design and created a G-rotor, which turned out to be 7 times more efficient than the Japanese competitor. Yeah. This next problem was to do with the problems with bearings. Now, when I was working for another engineering company there, and I said to them, like, there's this company in the Netherlands that is our client, and they want somebody to understand tribology. And my line manager said, well, guess what? Because I was about 30 at the time, they says, well, mathematicians hit their peak when they're 21. Surely you should not be, you shouldn't be going to try and solve this problem. I said, look, I've worked for their competitor before. Let me go and see whether I can try and solve this problem. Yeah. Now, what was happening in the Formula One is that if the bearings create too much friction, then what happens is, or potentially could happen, is that the wheels gets locked and the wheels gets flied off, and yeah, and then if you're in the middle of a Formula One race, that's the end of your race, because this is what happens: the wheels goes flying off. Yeah. So what we want to do is that we want to try and stop that from occurring. So but what the question was, the statement that was said to me was, there are problems which are too complicated to be solved by mathematics. And with me, I didn't believe that. I just carried on moving forward. Now, with what I did was, again, looked at this Reynolds equation, which has been taken by the engineers, been claimed by the engineers away from the mathematics community, and saying, look, we can actually model the bearings, how the bearings rotate, and look at where the friction is actually occurring. And by the way, what we need to do is that we need to embed our simulation within the Formula One simulation, so that we can actually have a more of a hybrid solution. And so what I did was, I had to write almost like a computer virus that actually changed the bearing simulation so that it was compatible with the Formula One simulation. And by doing that, and then doing an analysis, because this was in the middle of the Formula One season, because they were experiencing problems, that actual Formula One team in that year actually went on to win the championship. So the next problem is predicting the competitor's behavior. Now, one of the energy companies built a model that predicted a 5% growth in market share per month until it became number one. And that's what they're saying. Now, and I was there as a consultant, and I did question this and saying, wait a minute, you are building a model that predicts that that this company will have a 5% growth in market share per month until it becomes number one. And I said, but the thing is, you are assuming that the competitors would maintain their own strategy. They will not respond to the fact that you are taking 5% of market share each year. I'm saying, surely the competitors will respond to that. And I say, well, listen, there are things that you can't model mathematically. We can't model what our competitor is going to do. And I said, I'm sure there's a mathematical way of modeling what your competitor is going to do. And so, listen, and again, my challenge to the business is, your competitors will respond to an aggressive grab to market share. Yeah. And what they're saying, well, in their saying is that modeling is either wrong or lucky. We're only doing modeling just to support an argument for given by the directors, but it's either wrong or lucky. And I'm saying, look, I'm sure that we can model what the competitor is going to do. And so what I said to them is, have you ever heard the invisible boxer analogy? See, the question is, how do you win against a boxer who is actually invisible? Now, one of the strategies is that what you need to do is that you need to first engage that boxer, and from that you can actually learn from them. Do you learn, are they left-handed, right-handed, do they like working on the inside, or do they like jabbing? And then once you learn more about your boxer, how fast or how slow they are, then what you do is that you actually then move into the corner, you beckon them to come into you, and then when they come and you grab them, you turn them into the corner, you trap them in that corner, and then you have a great chance of knocking them out. The invisible boxer analogy. And the key thing about this, in terms of the energy companies, I'm saying is this: every time you encounter your competitor, you learn something about your competitor. You know that when you lose your customer to your competitor, or when you win customers from your competitor, and from that you can actually learn about your competitor's strategy. Now, by actually building what's called a Markov chain. So this is what we had. We had one energy company. This is a partial Markov chain, where it shows the movement from customers, from the probability of movements on customers from one energy companies to the others. This is for npower to British Gas, EDF, Scottish Power, EON, and Scottish and South Energy, and Southern Energy. We can actually look, by building a logical model, we can actually model what could actually go forward and model the competitor. And also we can actually look at previous data market share, and that can actually feed and validate the model. So what I did is I created a model that actually simulated market share, yeah. And what we had is we have two types of customers. You have a good customer. A good customer is a customer that pays the bills by direct debit and pays it straight away. And then they have a bad customer, what we call a angry bird. Now, an angry bird does not pay their bills by direct debit, and what they do is they look at the bill, they scrutinize the bill, and they write letters and they complain, and they refuse to pay if they think they're getting overcharged. Now, ideally, a company would want to have more good customers and less angry birds. Yes. So what they was hoping with this original model, they was hoping that they would have an increased market share until they become number one, and they thinking that none of the other companies would make a response to that. But what I did was I showed them is what happens if, for instance, if there is actually a uniform response by the other companies, what would happen to your market share? And also, what happens if the market leader actually made a response? What happens to your market share? I was saying if the market leader made a response, your market share would only remain very much the same. And what was shown in this trade magazine Utility Week was a certain company profit was up despite shedding 600,000 customers. That showed that actually the angry birds do exist. Now, using this this model, I was actually able to predict what the market leader was going to do in 6 months' time when government introduced new legislation. And what happened in 6 months' time? That the market leader actually did what the model predicted it was going to do. So, just moving on to the last example, Goldilocks and the Three Bears. So one day, a Royal Navy captain actually approached me and says, Nora, we've heard that you're a person that does real world mathematics. And I said, yes, I am. And I said, well, we have a problem with a certain future ship that is expensive to build, but is unaffordable to run. Do you know of a mathematical way of solving this problem? And I said, yeah, have you ever heard the story Goldilocks and the Three Bears? And he says, you what? And I said, Goldilocks and the Three Bears. I say, it's like this. See, Goldilocks, she goes into the house. It's part of the story where Goldilocks goes into the house. She eats his porridge. It's too hot. Eats that porridge. It's too cold. Eats his porridge just right. And saying, that's how you solve your problem. And he just looked at me and he walked away. And I didn't see him again for about 2 weeks. And then he came up to me and he says, Nora, would you like to follow me? And I said, I followed him. And I went into this meeting. And the meeting looked like this. And I said, hello. And I said, what's this meeting about? And they said, this meeting is about us possibly cancelling this future ship project. And we've heard that you come up with a solution. And I said, yes, I have. I said, would you like to tell us about it? And I said, yes. Have you heard the story Goldilocks and the Three Bears? And it says, I beg your pardon. And I said, yeah, Goldilocks and the Three Bears. See, Goldilocks, she goes into the house and she eats his porridge. It's too hot. She eats his porridge. It's too cold. And she eats his porridge and it's just right. I was thinking, and that's how you solve the problem. And they said this to me. Do you realize that this problem is of national importance and you're coming up with some sort of nursery rhyme? I said, okay, wait a minute. Let me be more specific. What you need to do with that ship is you get this design, you link its capability to this design, to its cost, and that will create a whole series of nonlinear mathematical equations. Then you write an algorithm and then you say to the computer program, right, design me a ship that's not too hot, not too cold, just right. And here's an example. And I looked at it and I says, oh, that's quite interesting. That we think that actually might work. See, now that was over 10 years ago. See, the question is, would you like to see what that ship looks like today?
I must admit, I held my breath as she came here through the harbour entrance because it's so small.
We're a proud Navy family coming here to see the ship going in. My husband had worked on the programme, so it's been kind of a lot of our lives. In fact, our wedding cake was the Queen Elizabeth carrier.
It was brilliant, worth waiting for. It's a brilliant experience.
It'll take some time to build up the operating envelope and our understanding of the complexity of operating a ship of this scale. But we've done a lot in preparation for that, working with both the French and the United States Navy.
Yes, the HMS Queen Elizabeth. Now, my name, as well as other contributors to this aircraft carrier, there's a placard which our name is actually there, and our name will be there and remain there for the next 50 years. So that is showing mathematics in action. Now, with my representation of mathematics, like I said in the introduction, that I was named one of the UK's top 100 scientists, and I was cited for developing mathematical applications for industry. So I'll go back to June 2004. Like I said, I went to the first IMA Younger Members Conference, and we was talking about how we could make mathematics much more appealing to the general public. And one person who had went to Oxford, Southampton, worked for the Bank of England, said, they would never defend mathematics at a cocktail party. Well, and I said this to them, and this was an important. He said that, well, if a radio DJ said that mathematics was boring, who among you would stand up and defend mathematics? None of them put their hands up, and I said I would, and I did, because a year before that, I actually went onto a radio station to defend mathematics, and speaking to the executive director then, they said, well, could I write an article for Mathematics Today? And I did say that. And I said, a good friend of mine who is a non-mathematician once told me, if mathematicians are not enthusiastic about mathematics, then who else on earth will be? I say again, if mathematicians are not enthusiastic about mathematics, then who else on earth will be? So, in conclusion, not only should we build a powerful mathematical identity, we should embrace it. Conclusion, leadership is not a position or a title, it is action and example. Mathematicians, the question is, who are we? I say again, mathematicians, who are we? And I'd like to thank you, and I'd like to thank all those organizations that helped me from when I achieved my PhD in 2014 to becoming president in 2020. Thank you. That was the building a powerful mathematical identity. Thank you.
Thank you very much, Naira. It's hard to get a full applause on a Zoom meeting, but I think that was a fantastic talk and people have enjoyed it very much. If you can raise a virtual hand for questions and/or put it in the chat. To raise your virtual hand, there's at least on my screen towards the bottom, there's an icon that says reactions. If you click on that, then you get an option to raise your hand. So I have somebody, HM, has raised a hand. I'm not sure who that is, but if you unmute, please ask your question.
Hello, good afternoon. Just 1 second. I'm just making my mic work properly. I hope that's okay. Dr. Chamberlain, Professor Chamberlain, that was a very interesting talk. Thank you. My name's Hassan, actually, and I'm a mature student at the University of York doing mathematics, pure maths. And I returned to mathematics from, strangely enough, studying law in another country because of my interest in data science. I guess my question concerns something that you've raised, perhaps, tangentially, which is feeling a little bit, my path to this degree has been a bit unusual. Like I said, I've been a humanities student all my life. I hated maths in school in Pakistan, and now that I'm studying it, I love it to bits. But I am intimidated, to be quite honest, by statements such as the one that you repeated, which is the one that, scientists hit their peak, mathematicians hit their peak at 21 and so forth. And I was wondering if you might have something to say about somebody or students who come from slightly unconventional backgrounds and might not have had the preparation. I didn't do A-levels in maths. I did open university modules. And so I often feel like my preparation is lacking, especially when you think about the highly rigorous and advanced areas such as analysis. It feels like I haven't gone through the usual mill. And sometimes I find myself unable to think of, for example, the integral of 1 over x squared plus 1. And then I think, well, okay, so that leads to a loss in confidence. So I'm wondering if you might have something to say about that.
Yes, I mean, I certainly do. I mean, thing is, like say, in terms of, when I say mathematician hits the peak at 21, that's what people said to me. That's not a statement I endorsed. And, one of the things that I'd say is that, if you want to look about unconventional, now my route to becoming president of the IMA is unconventional. I did a part-time PhD. I did my first degree at Coventry, or what was then called Coventry Polytechnic. My route has been unconventional, but what you bring, Hassan, is that you bring something very different to the table. Diversity in mathematics, diversity in thinking in mathematics is so important. Sometimes when you're having a group of people who, let me use the example of mathematical modeling, that may go to one university, taught by the same professor, all think the same, and then are tackling in the mathematical model in the same way, same thinking, and not thinking outside of the box. That could cause a problem. Now, what you're saying in terms of where you're coming from in terms of law. I mean, I can see when you finish your education, I know that there'll be in so many data science firms, that the law firms, that will pull your hand off, because you have that advantage of understanding law and humanities, but also having an understanding of that mathematical technique and how the two can actually combine together. So, you have a lot to bring to the table. As I regard you as a mathematician, and you have so much to bring to the table, because mathematicians, we're a diverse community, but we have this common thing called mathematics that unifies us. Does that help you in that answer, that question?
Thank you. Yes, I suppose because I followed you with some interest when I heard you were giving the talk, and I started reading up on your background. I was aware that you'd worked and studied, so you have a foot in industry as well as in pure mathematics. That's absolutely correct. So thank you. That really does help a great deal. And I guess I should mention that my display pic is of the interior of the Blue Mosque at Isfahan in Iran. And as you know, Iran's produced, so I look to that as inspiration. The Iranians, not that I'm Iranian myself, but Muslim mathematicians, for example, like Al-Khwarizmi, who invented both algebra and the algorithm, and the work that you see in the Islamic world. I think it might be a useful thing perhaps for people of all backgrounds to be aware of what their ideological or racial ancestors have done in the field, because we tend to hear the names Cauchy, we tend to hear the names Liouville and Sturm quite a bit, but I suppose other contributions tend to be a bit unheard of, if you like, in the curricula, and that's something in mathematics as a whole, I found.
Okay. I mean, yes. I mean, broadening mathematics. I mean, no doubt you probably, people that are familiar with my work on the Black Heroes of Mathematics and conferences is that, and making it broader. I mean, I'm one of the people that research all cultures about and their contributions to mathematics. So thank you very much indeed for putting that picture up. And respect to there.
Thank you.
Yes, thank you. And there are a couple of comments in the chat as well. One person has pointed out George Green, who's known to us for vector field theory and Green's theorem and so on, who was the son of a miller based around Nottingham, and only went in his 40s, I think, to Cambridge. and started to produce his results then. And then, of course, there's the field medalist, Miriam Mirzakhani, who was from Iran too, as an example of diversity.
Yeah.
Yeah. Other questions? So I think one of the questions that disturbs me is when I've looked around undergraduates in the few places I've taught around the UK, I'm very conscious that we have relatively few people, particularly of African and Afro-Caribbean origin in our classrooms. And I wonder what we can do to really improve that. It's I think, a very important issue for us. I can see with other groups, whether it's women or people from other ethnic backgrounds, that the numbers are on the way up, even if they're not increasing rapidly. But that's a particular issue for us. How do you think we can target that?
Well, I think there's two number of things that can be done. Right, one actually going, doing outreach, going to their schools, telling them about the powerful and the wonderful world of mathematics. And two is also is actual the awareness. People, sometimes when people say role modeling is important, and they're saying, people say, well, where are the black mathematicians or mathematicians of African diaspora? And people say, well, where are they? But in my 5 years research, I've been finding they're there. It's just a case of they're so scattered, and what they're doing is sometimes is not well known. I mean, a couple of months ago, I came across a mathematician based in Canada that has a research group named after himself, who's looking at using machine learning to look at the strategies of rolling out the vaccine against COVID across the whole continent of Africa, and he's been appearing on the Canadian national news. And I'm thinking, no, we don't really know about that. But you're having a number of those mathematicians that are excelling at mathematics, using their mathematics, and it's just a case of we're not generally aware of what they're doing. And I suppose that's one of the key things that I was, one of the conferences that I'm actually involved in is, the Black Heroes of Mathematics, which I do with the ICMS. That's one of the important things is we're doing. We're showcasing the achievements of Black mathematicians, both present and future.
Thank you. I think what I'll do at this stage is that we will formally close the talk, because I'm aware it's past 3 o'clock, and I know some of my colleagues have other
there's another question by Frank.
Yes, but what I think we can do is then carry on with the discussion for those who would like to stay.
Yeah, so if so, then let me also say a few words. I want to thank you. It was a pleasure to host this event, as I told you also before. I think that was the most inspiring talk I've ever heard in my life, by the very far, more or less. So that's and I'm sort of I sort of think that most of the audience think that way. So that's I thought I would remark that.
Okay.
Yeah.
So, can I tweet that?
Yeah, I guess.